Yes, sir. Now it is visual, sir.
Okay. Thank you. So, first of all, I am very thankful to the organizer of this FDP and invited to deliver a lecture on this very prestigious and very important topics. So, the talk of my topic is the solar PV and grid-based on-board charging solution for electric vehicle. So, in on-board, when we talk about the on-board application of electric vehicle, so one of the very important parameter we have to keep in our mind is the compactness of the charger. Because we are our charger will be inside the vehicle, means in the premises of the vehicle. So as we know that there are already weight of the battery system in the electric vehicle, so then charger weights also there. So if we want to employ the charger inside the vehicle in case of on board, so it should have a very low weight and less volume. So in that talk, I will discuss the how the compactness of the onboard charger we can achieve in electric vehicle. There are many onboard chargers are already available. The conventional onboard chargers, where means we do not much care about the compactness of the system. So in this talk, I will how various way we can achieve the onboard charging solution with compactness. So as one, when we talk about the onboard solution, so onboard solution is also constrained by the power level also. So because if we want to increase the power level, automatically the weight weight of the charging system will increase. So how can we reduce the weight of the charging system? Means by enhancing the compactness, as well as how can we increase the power level
మన
of the
సబ్జెక్ట్
charging
బేసిక్
system?
ఎలక్ట్రికల్ అండ్ ఎలక్ట్రానిక్స్ ఇంజనీరింగ్. ఇందులో పార్ట్ ఏ ఏంటంటే బేసిక్ ఎలక్ట్రికల్ ఇంజనీరింగ్, పార్ట్ బి ఏంటంటే బేసిక్ ఎలక్ట్రానిక్స్ ఇంజనీరింగ్. సో ముందు పార్ట్ ఏ చూస్తున్నాం, బేసిక్ ఎలక్ట్రికల్ ఇంజనీరింగ్. ఇందులో యూనిట్ 1 ఏంటంటే డిసి అండ్ ఏసీ సర్క్యూట్. ఇవన్నీ డిసి సర్క్యూట్ టాపిక్స్, ఇవన్నీ కూడా ఏసీ సర్క్యూట్ టాపిక్స్. ఇందులో ఏమన్నాయి అంటే ఎలక్ట్రికల్ సర్క్యూట్ ఎలిమెంట్స్ అంటే
Participant
రెసిస్టర్,
might be,
కెపాసిటర్.
you can switch off your mic.
Ohm's law and
Hello.
its application, KCL and KVL, series connection, parallel connection, series parallel connection, superposition
Hello.
theorem, ఇది మీద సింపుల్ ప్రాబ్లమ్. ఇవన్నీ కూడా డీసీ సర్క్యూట్. ఇది చదువుకుంటూ ఒక ఎస్ఏ అనుకో. నెక్స్ట్ అన్ని ఇది కూడా ఏసీ సర్క్యూట్ చూడడానికి.
So this is the architecture of an typical electric vehicle charging system, as well as the propulsion system also. So we will charge the vehicle by a single phase supply or a three phase supply. So depending upon the power level, there are different types of the level of charging. So in a charging, definitely there will be a AC to DC converter. Then another stage is the power factor correction stage. Then a third stage is the DC to DC converter, which provides adequate battery voltage and current to the battery. And there is a bidirectional DC-DC converter which is connected between DC link and battery, which is required in electric vehicle to power flow between DC link and battery, because from the DC link to the battery, in case of the regenerative action will take place, so power can be fed back to the battery also. And there will be here a DC-DC converter which is used. It is usually high step down converter from DC link to the a auxiliary supply needed in the electric vehicles for the lighting, heating purpose in the vehicle. So it will be usually high step down converter, high step down. So motor, as we know that there are popular motors are in electric vehicle are induction motor, PMSM motor, BLDC, and SRM. These widely used motor in the electric vehicle. So this is the another block diagram of a electric vehicle where solar and grid both are used for charging in onboard application. So first and PFC stage combined in one block, AC DC plus PFC stage, and there will be a bi-directional converter between battery and DC link. And from solar, if it is charged with the solar also, so MPPT converters required. And in this arrangement, another energy source has been shown, supercapacitor, which is connected at a DC link through a high gain converter, or it can be also connected to the normal DC-DC converter. Normal DC-DC converter or conventional DC-DC converter, whose duty ratio like D 1 upon 1 minus D or D upon 1 minus D. So high gain converters require sometimes if the supercapacitor terminal voltage is low. So these are the power levels in electric vehicle charging system. So level one charging system, it is also known as the slow charging. It is from home supply, that is a single phase AC supply which range from 120 volt to 230 volt depending upon the whether in which country we are living. In US, as we know that 110 and 120 till 120 volt 60 hertz system is employed. In India, 220 to 240 volt system we use. Power level in between 1.4 to 3 kilowatt. It is that's why it is a slow charger. It will take, so depending upon the battery kWh capacity, charging time will vary between 8 to 20 hours, and it is employed for home overnight charging. Level 2 charging comprised of both single phase and three phase AC charging system. Uh, its rating may vary depending upon the voltage level. In usual rating, it's 3.3 kilowatt to 20 kilowatts, and charging time may be between 3 to 8 hours. It may be residential also, it may be public charging, it may employ at home also, at as well as the workplace also. Then level 3 charging system, which is DC fast charging, where DC supply voltage may vary 400 to 900 volt, even it may more, the range can be mm, the range of maybe more, means it's maybe 200 to 1000 volt also. And power level vary up to 350 kilowatt. So these are the category of the charging power level. So level 1 is used for onboard application only. Level 2 at some, it's till 22 kilowatts we can use for the onboard application. Beyond that 22 kilowatts we will not design for the onboard application. And level third, definitely it is the outboard charger. So here first, how a I'm showing a block diagram how from the conventional charging system to from the conventional charging system, how we can achieve a low cost and compact onboard charging system. So you can see the block diagram here, a conventional single stage onboard charging system where AC DC plus PFC stage combined single in one stage and connected at a battery, at the output is connected to the battery. Then bidirectional DC DC converter, which is connected between battery and DC link. So it is mandatory this bidirectional DC DC converter. So some of the authors have gave the solution how to combine this AC/DC PFC stage and bidirectional DC/DC converter in a single converter, so that some of the components can be reduced especially magnetic component. As we know that in a power electronic system, magnetic components is the one of the heaviest component in the whole system. So if we are reducing by combining these two converters in a single converters, how how is it possible to combine it? Because there are different modes of operations in the electric vehicle. As we know that charging, propulsion, and regenerative braking. So charging and charging is completely uh, disintegrated from the propulsion and regenerative braking operation, because when charging will take place from the grid or any other sources, so it means when vehicle is at standstill condition. Okay, so the charging converter can be utilized with the propulsion converter, okay, to incorporate in such way that uh, to form a new converter or integrated converter, so that overall system weight can be reduced. It is possible. So here AC DC PFC stage and bidirectional DC DC combined to form a integrated converters, so that all the modes can be achieved: charging, propulsion, and regenerative braking. So this is the first uh, integrated solar PV and grid-based charging solution for onboard application, where all the modes we are achieving. All the modes: charging, propulsion, and regenerative braking. So this is the rectifier, and this is the solar PV which is connected at the output of the rectifier. So these rectifier is connected for the grid, and solar PV is connected at the output of the rectifier. In this solution, in this charging solution, there is a one limitation also, that's grid and solar always operates in a complementary fashion. Complementary fashion means either grid will charge the battery, or solar will charge the battery, because two sources connected at the same point and their voltage may be different, so we cannot operate simultaneously. So this system is derived from the SEPIC converters, isolated SEPIC converter. So in a grid charging, this is the battery. This is a kind of a three-port converter, which is mentioned here: port 1, port 2, and port 3. So in a charging operation, either solar or PV, the complete operation will be like a SEPIC converter, isolated SEPIC converter. In a propulsion operation, it operates as a flyback converter. Flyback. So the switch S2 will be operated in a PWM, and magnetizing inductance of the transformer will store the energy when switch S2 will be off. S3 switch body diode of switch S3 will transfer the energy to the this DC link system. As we know that after DC link there will be an inverter and motor and drive system of the electric vehicle. So we will not discuss those part in this particular solution. So control strategy, we have to understand the control strategy of such operation. So it is very simple, because solar PV with there is this isolated SEPIC converter operated as a MPPT converter. So we will measure as the MPPT, any MPPT techniques we can employ. For the charging from the grid, whatever the charging power we can take PV reference. So it, by dividing the battery voltage, it will generate a battery reference current. After that, this is the a conventional PFC control strategy for the converter, which is well known and established in the literature. So we will achieve the power factor at a grid side unity, so that there will be a less burden on the source. Burden means if power factor will be poor, then reactive power consumption will be more from the uh, grid side. So this is the operation which already I am not discussed the two means detail of each operation, because here the converter operates only in as a isolated, whether from the grid. If grid is active, then switch S1 will be in PWM, or rest of the operation is same as already we know about. And in case of solar PV charging, when grid is not available, so again this converter operates as a CPIC converter. So in propulsion and regenerative braking also, I discussed with you that switch S2 will operate in a PWM, and body diode of switch S3 will come into the picture for the transferring of the energy from the stored energy in the inductance transferred to the DC link. Okay. So similarly, in regenerative braking, again it acts as a flyback converter. Switch S3 will be in PWM, and body diode of switch S2 will come into the picture, and recovered energy from the regenerative action will transfer to the battery. So now I will come to the its simulation as well as its experimental results. So simulation results has been shown uh, with 220 volt grid supply, and here we can see, and the charging power is the 1.2 kilowatt. So there will be a battery voltage here. This is a grid current and grid voltage are in same battery voltage. It is a single stage system and single phase, so low frequency harmonics will appear. Low frequency means till 100 hertz, 100 hertz frequency. It is naturally, we know that from the power balance theory, that in battery, if it is a single stage system, so 100 hertz frequency will appear in the battery current, and it can be suppressed by the connecting a large inductance at the battery terminal. So there will be always a compromise between the size of the inductor at the battery terminal, uh, because the how much we want to reduce the ripple, and the size of the inductor. Okay, so now I will come to the solar PV mode. In solar PV mode, only solar is used to charge the battery. So this is the PV power, and which is generating 800 watt, and this is the battery voltage and battery current. So this is a experimental setup of this complete system. This is the 48 volt battery is used here with IRF 460 460 MOSFET has been used to design the driver circuit of the switches. So now I will come to the propulsion mode of operation. In propulsion mode in simulation, it has been shown as the a load has been changed from 1 kilowatt to 2 kilowatt, and DC link voltage kept at 400 volt. So this is the objective of the propulsion mode. First, we maintain the DC link voltage constant. Then other motor control concept will be different. Okay, so first objective is to control the DC link voltage, and in experimental in experiment also, here a DC link voltage has been kept constant. It is a 150 volt we have taken in a experimental platform, and this is the at a different loading condition here how the battery voltage is battery current is changing here, and load power has been changed from 400 to 500 watt, again 500 to 400 watt. In a regenerative braking operation, we can see here uh, DC link voltage has been varied to charge the battery. This is the battery current, and here this kind of flyback can be operated in a buck and boost both mode. So you can see initially above the, if here unity, because turn ratio has of the transformer has taken unity. So d upon 1 minus d will be the, if turn ratio is unity, so this will be the voltage gain formula of the between input and output. So above the 0.5 uh, duty ratio shows that boost operation, because at the DC link voltage low, so we require boost operation. If DC link voltage high from the battery voltage, we require the buck operation. So both buck and boost operations shown in simulation and as well as in a hardware experimental. So this is the another solution for the low cost integrated onboard and compact charging system. So in the previous work already it has been shown uh, that there was one limitation: solar PV and grid cannot operate simultaneously. Here solar PV and grid can operate simultaneously to charge the battery, and rest of the things are same. Here both isolated SEPIC and non-isolated SEPIC is utilized to in the system. Okay, so here by solar PV, it is a 4-port converter: port 1, port 2, port 3, and port 4. So grid and battery, grid and solar PV both are used to charge the battery. Solar PV is connected to non-isolated CPIC. So we have to understand its control strategy here. It is important. So first we will achieve the MPPT operation through the non-isolated CPIC, and there will be a reference charging power for the battery. So there will be a reference. This reference power will be uh, the reference power will be subtracted from the uh, solar PV power, and remaining power will supply from the grid. Okay, so we will measure the grid power, and this is which will be the grid reference power, and this part will for the PFC. So first our objective to charge the battery from the solar PV. If the all the power is not made by the solar PV, means the charging power, so rest of the power we will take from the grid. So again, in this operation, if it is operates independently in grid mode, so it will this converter operates at the as an isolated SEPI. If it is solar PV is only is used to charge the battery, so the complete system operates as a non-isolated SEPIC. Non-isolated SEPIC, and maybe both sources can charge the battery simultaneously. I'm not going to details of these operation of the converters, because these are the conventional only operation. In a regenerative braking, in propulsion mode, this converter operates as a boost converter. So switch S7 is operated in a PWM mode, and stored energy in inductor will transfer to the DC link side. And in regenerative braking mode, because as we have assumed that DC link voltage is higher than the battery voltage in this particular solution, so so buck operation is required, then switch S2 will be operated in a PWM mode for the buck to achieve the buck operation. So this is the stress analysis of the complete converter system. So which switches here, the means what is the voltage and current stress on the switches. So maximum voltage which appears on the switch S7 is VG max 2 plus VB, whatever the battery voltage, whatever the grid peak voltage. Here, VG max means the grid peak voltage. So we have to take care about these stress, because while selecting the switches, we means select in such way that its switch voltage rating must be higher than this switch grid some of the a grid voltage plus grid peak voltage and battery voltage. Similarly for the current also. So now I will come to the result section. So these are the parameters which is used during the simulation and experimentation. So these are the hardware parameters. So again, charging power has been taken here 800 watt, complete reference charging power, P reference. Okay, so this is again a single stage system. So there will be a low frequency ripple in the battery current, and this is the grid voltage and grid current are in same phase and same shape also. So it has a low TSD as well as a high power factor. So here we are seeing that a high powering unity, we have achieved unity power factor frame, power factor, and TSD is around 4.4%. So some of the intermediate result has been shown here. Middle capacitor of the SEPIC converters, voltage isolated SEPIC converters, and this is the inductor current waveform, and this is the switch voltage waveform. So these switch voltage again, whatever. So I already discussed in the stress analysis. The voltage across voltage on the switch SA1 will appear as the VG max plus VB. That's why its shape is like this way, because VG will vary uh, from 0 to some value. Okay, it's a peak value only. Again, here experiment in this only experimental result have been shown with the change in the grid, load power in propulsion mode. This is the propulsion waveform. So DC link voltage kept constant here, and this is the regenerative waveform here. DC link voltage has been varied to charge the battery. Okay. So now I will come to the another form of compact integrated on-board charging system, which utilize the machine winding in the charging system. So as we know that machine winding uh, is in very beginning of the electric vehicle research, machine winding has been used to machine winding utilized in the charging circuit, because this feature we are achieving uh, because charging, propulsion, and regenerative braking operation. So charging is completely separate from the separate operation from the propulsion and regenerative braking action. So this is a very interesting as well as a very in the very early research, so many US patent has been published, and such kind of system already used in the in electric vehicle which is in the market. So this is a schematic of the integrated on-board charger. When we are machine winding, we are utilizing in the charging circuit. So whether motor maybe any kind of electric motor, whether it is SRM or PMSM or induction motor, so inverter and motor winding, these two system forms as sometimes a boost converter, interleaved boost converter, buck converter, interleaved buck converter. What with the some reconfiguration approach, we can form the different kinds of the power electronics converter. Mainly these are the either it is will be the either it is a boost converter or buck converter. Further it will maybe it may be two phase interleaved converter, two phase interleaved boost and buck converter. So this is another block diagram of such system. So not only machine winding, machine winding here, machine winding and battery is used to charge the battery. Sometimes with machine winding, another converter in can be interfaced with the system to increase the power level. And for the single phase or three phase AC charging, type 2 connector is used. For the DC, if there will be a DC charging only, then TEDMO will be used as a connector. And for if there is both AC and DC source are there, like again grid and solar PV, so CCS2 combo can be used to as a connector in the electric vehicle. So why we are going to use these machine winding concept in the electric vehicle charging system? So we can see here different kinds of electric vehicles model shown here. How the power rating of this is the motor power rating in EV model is the induction motor based EV. Here the power depending upon the different model of the electric vehicle, the power level of the motor rate in this Nissan ENV 280 kilowatt, Tesla Model 3 has the 250 kilowatt motor, Mahindra E Vertio has the 31 kilowatt, like that power labels are shown. So these are the motor power rating. So motor power rating on this power label. Again, it is designed for the propulsion operation. So connected motor is connected to the inverter. So inverter rating it will be definitely in accordance with the motor rating. Okay. Okay, so those high power rating already available, means motor winding as well as the inverter. So we are forming the motor winding and inverter as a converter for the charging purpose only. Okay, to charge the uh, battery. Again, PMSM based EV we can see here the Nissan Leaf E Plus motor rating is 160 kilowatt. Chevy Bolt has a 149 kilowatt. So like that, Zero SR JF 14.452 kilowatts. These are the some models which I have only just shown because of the how the motor power rating in these types of the electric vehicle model. So look it first. This is the a motor winding. This one induction motor winding. This is the inverter. This inverter connected because inverter is present in the electric vehicle during for to achieve the propulsion operation. Okay, so as we already know that uh, propulsion and charging are completely complementary operation in the electric vehicle. When charging will take place, propulsion will not take place. Okay, so here battery is used to supply power during the propulsion operation. If vehicle is at rest, so here by some reconfiguration approach, switch K1 and K2 and K2 dash is closed during the charging operation and K1 will be open. So you can think about if switch K2 and K2 dash will be closed, this circuit will form a two-phase interleaved converter. Okay, two phase will be used in this particular solution. If it can be used as a three phase interleaved, we will see later how we can achieve. So in this case, because when these switches will be closed, so current will flow from these two inductors, and by uh, concept of two phase interleaved boost converter we can utilize it here. So how these important things already many researchers achieved in the past in the uh, 2010 and 2011 only, and some very early research also done in the machine winding around this particular what patent. This is published in 1994. This is the US patent. So now here I'm coming to the another configuration of the machine winding which is used in the charging circuit. So here we are assessing the neutral point of the motor. So in this particular solution, we have not achieved the neutral point. So neutral point assessing is a challenging task in the motor because it is not readily available. Okay. So, but here, if we are achieving here uh, neutral point assess, so we are not utilizing any relay and contract circuit to open and close the machine winding during charging and propulsion, because if we have not assessed the neutral wind, here we have arranged some other mechanism to achieve the charging and propulsion operation. Okay, so we have not used any relay circuit breaker like that. A single phase supply can be connected here. Okay, in positive half cycle, one um, uh, uh, both. Okay, yes, in positive half cycle, one we can utilize one circuit, and negative half cycle we can utilize another circuit to charge the battery. If but this particular configuration is possible only when there are two motors in the two wheel drive system, because maybe there is one motor for the front wheel and another motor for the rear wheel. So in such kind of this solution is possible. So here in these two system we are utilizing single phase supply. In this also, in this system also single phase grid supply used to charge the battery. There may be a possibility uh, here another approach which is shown here for integrated charging system. Again, it is not utilizing the assessing the neutral point. So in a charging mode, this is the rectifier which is connected uh, for the to charge the battery. Okay, here a rectifier system will be there. Okay, if we have rectifier system, we are not utilizing any mechanical switches to open or close the motor winding. Okay, in during the if you will of the grid means these rectifier, so battery will connect it to the DC link, and this will be the arrangement for the propulsion operation. Okay, so in first three circuit, what we have seen, uh, these are they are using a single phase supply system. Okay, single phase supply to charge the battery, and sometimes it is also a two phase interleaved converter will two phase interleaved boost converter uh, will be formed in this, because current will flow this like this way. So one important thing, one another issue which arise when when we are using the machine winding in the charging circuit. Okay, while during the, as we know that a motor, if PMSM machine is there and it's already has the permanent magnet on the rotor, and there is the current in the stator winding, so there will be interaction between the these current will generate the flux, but sometimes this current will be the DC current, sometimes it will be the pulsating DC current. So there will be a torque production will be there during even in the charging, during the charging. So this is the torque equation during the charging for this particular mode of operation. Okay, so we in phase A current is the two times of the phase B and C currents. Okay, as this is the standard formula for the torque production in the in PMSM motor in terms of ID and IQ. So ID and IQ shown here. If we by putting the IA equal to 2 times of IV and IA and 2 IC, so when we keep this ID and IQ in this equation, we will get this equation. And as we know that this is the charging torque. Charging torque. This torque must be zero. Otherwise, during the charging, uh, motor will some kind of a hunting will take place. Okay, this this torque will zero when theta equal to 90 degree. From this relation, you can see that cos theta 90 equal to 0, sine at 180 degree will be 0. Okay, so how we in perform the propulsion operation? Okay, we have to ensure that theta electrical of the machine must be 90 degree. Okay, then in one interesting thing the author have been shown is this: if it is purely DC supply, if, let's say anyway we are not utilizing the if it is a equal DC current flow, then this expression means IA equal to IB equal to IC. So ID and IQ will be in a such way that this torque automatically zero. Okay, it means if you are utilizing as a two-phase interleaved, theta electrical kept to be 90 degree. Okay, theta electrical should be 90 degree, and if equal current will be there, IA equal to IB equal to IC, this is automatically this will be zero. You can derive this equation from when you apply sin C sin D rule. You will find that for IB IC is equal. I have derived and seen it. Now I will come to the another topology here. In this topology, single phase supply has been used. All the three phase, all the three types of converter which I have shown here, a single phase supply has been used. Now, if you want to increase the more, because the this motor and I have shown motor has these inverter have high rating, so we are not utilizing its full capacity. So if we onboard charging has a limit of the 22 kilowatt, which I have shown in the level 2 charging, but from the single phase rectifier we cannot achieve the 20. So we have to employ a three phase circuit. So to increase the power level, we can connect a three phase AC DC converter. Okay, three phase AC DC converter here. So now I will come to another solution. Here only DC supply is used. Okay, DC supply is used. DC means the solar PV has been used to charge the battery using the machine winding. Okay, so it is here we form the already I told these motor winding and this converter means inverter switches and motor winding either can be form a interleave boost converter or interleave buck converter. So it is here I have form interleave buck converter. Okay, a diode is connected between battery and neutral point. So this particular configuration requires to assess the neutral point, because this battery we cannot connect to the neutral point. That's why here a diode is connected. and this switch will take care for the battery is connected to the DC link when propulsion mode operation is required. This bidirectional switch is required. Bidirectional switch can be realized in many other ways also. I have realized in this way. So operation, this is the operation of the converter interleaved, three-phase interleaved buck operation. This is again conventional things. So operation I will not discuss in the detail of, only the concept behind it, uh, that uh, we have used it as an interleaved buck converter, how the some circuit arrangement required to achieve the propulsion and propulsion operation and charging operation. And I also here assert that why I have taken it as an interleaved buck operation, not interleaved boost operation. Because if solar PV, not only I'm talking about is here a solar PV will be there, it can be any DC source, doesn't matter. Okay, so DC source, if, and this rating will be motor winding and uh, motor winding and inverter has high rating. So what in case of a DC supply, you can any DC source will be outside there, and you can use it. Okay, you can use to charge the battery whatever the motor winding and inverter rating will allow. So it may be 100 kilowatts also. Okay, 100 kilowatt uh, uh, power charging power level. So there will be a very high current at the hello. So there will be a very high current at the uh, output side. So buck converter is very popular for the uh, when there will be a high current at the output. So such buck converter is used there, because but uh, in it is naturally it can carry the high current in buck at the output side. So so high current will be there. So switches will also face the high current. So ZCS zero current switching scheme also we can employ in inverter switches. So this is the conventional ZCS operation has been achieved in this converter, which we will see in the result. So we can see here a zero current switching at the turn of the at the these falling edge of the PWM. The current is going to zero of the switch. So ZCS operation has been achieved. And different solar PV variation, solar PV from the solar PV 500 to uh, 1000 solar radiance to the 500 solar radiation. So we have shown here by applying the step change. So solar PV voltage, solar PV power and has been shown, and corresponding battery voltage, battery current has been shown here. And this is the inductor current waveform there. These are the three-phase inductor current which is 120-degree out of phase. Okay, so the complete configuration is done with the Opel RT. This is the switch voltage across switch S1. So through the ZCS operation, we there will be a efficiency improvement around 2.2 to 2.5% if you compare to the hard switching. So now I will come to the another topology, which is extends the topology which I have shown the solar PV DC supply. It is for the when AC supply is there. So we when we utilizing the AC three-phase AC supply, so add-on AC DC converter we have to place in the premises of the vehicle. So again, maximum charging power, because we for the label 2 is the 22 kilowatt in onboard application. So for this converter, 22 kilowatt charging power will be there. So this is the control of DQ control theory of the AC DC converter. It is conventional only and well known, established in the literature. And interleaved converter control strategy is used here for the second stage. Switches are 120-degree apart, 20-degree phase difference between the switches turn on time. Okay, these are the some real-time simulation waveform, real-time experimental waveform. Okay, so this is the grid voltage and grid current are there. This is the inductor voltage waveform. Again, in this also we have at the second stage interleaved buck converter operation there. So we have achieved the ZCS operation, and with the step change in the reference power, how the here the grid current is varying, and this is the DC link voltage. DC link voltage kept constant only. And another law, when we have seen that law from the loss analysis point of view, there is a lot of inductors is there. So in a different losses has been shown. Semiconductor loss in the interfacing converter means AC DC converter. Okay, means what are the semiconductor losses? And semiconductor loss in propulsion converter is 25%. Inductive loss in propulsion system is there is around 27%. And very small capacitive losses are there. It is around 1%, and 3% is the miscellaneous losses. This loss analysis has been theoretical loss analysis are there. Then now what I have shown in a first the solar PV, a kind of a DC source has been used to using machine winding. Three-phase source has been used to charge the battery. Charge the battery. Now this is the combination of both. A three-phase converter, a DC system will be there. By assessing the neutral point, so a DC supply, whatever with the DC, it may be the solar PV. So this is the arrangement of the combinatory AC DC charging system. So this is the simulation parameters for the this particular system. So we can see here 120 uh, sorry 90 plus 19.4 kilowatt system has been used have been designed, means 90 kilowatt for the DC power and 19.4 kilowatt. Some of the uh, convention takes the label 2 charging type 2 charging limit. Type 2 charging limit for onboard application is 19.4. That's why this particular researcher has been taken 19.4 kilowatt as a AC solution, and for the DC it will be for the 90 kilowatt charging system. Okay, so as we increasing the DC power level, so current battery current will be according to we can see here you at when there is no sorry when 18.9 kilowatt power is there, so battery charging level at a 0.4 C, as the power level of DC supply is increasing because the AC will be fixed. So as DC power will increase to 48.16, so its a charging level will be 0.9 C. As like this will it will increase. So again, this is another work which is shown here. AC DC charging approach with solar PV, but we can see here, here solar PV is utilized with machine winding, and this inverter has a interleave, two-phase interleave. So in this particular control strategies shown here, the reference, it is interesting. Reference power will be used for the charging. So solar power, we will measure the solar power and subtract it, and then it will generate a grid reference power. And grid reference power will utilize to remaining power is taken from if the solar PV, all the reference power is not paid by the solar PV. So grid will use to charge, grid power will utilize to charge the battery. So here a unity power factor, to achieve the unity power factor at grid side. So arrangement has been used towards, this is the outer loop, this is the inner loop, this is the hysteresis loop is there, and depending upon the error signal, switches on and off condition will take place. So we will see its operation, and this complete uh, system will operate as uh, in AC DC buck converter. Okay, then we can see here, if any upper switch will be on, it inductor will store the energy. Okay, and if all the upper and lower switches will turn on, then the this diode will turn on to circulate the current between inductor and battery. Okay, so this is the operation of AC-DC converter. Again, operation of this side is very simple. It is act as a two-phase interleaved boost converter. So now I will come to here. Maximum power for charging from the grid has been taken 19 kilowatt, and maximum solar PV power has been taken 101 kilowatt to achieve the 120 kilowatt total charging power level. Okay, so we can see here, if a reference power from 110 kilowatt to 120 kilowatt has been changed, 101 kilowatt of solar PV. So how the grid current has are changing, and it is maintaining the unit a sinusoidal shape, and corresponding reference the battery current is shown here, battery voltage and battery power. So when we are using solar PV to charge a dynamic analysis has been implemented. Solar PV, solar radiation has been varied from 200 to 600, and then 1000, and corresponding PV voltage, PV power is changing. And this is the again battery, corresponding battery voltage, battery current, and SOC of the battery is changing. This is the real-time experiment waveform. Uh, Again, with 19 kilowatt grid power, grid voltage, and grid current are in same phase. When grid power is reference power change from 110 kilowatt to 120 kilowatt. So how the grid current is changing. So grid voltage and grid current in this situation are same phase and same shape. It shows high power factor at grid side. This is the variation in the solar PV irradiance, and corresponding solar PV voltage, current, and power. Then this is the reference power after the reference power variation. This is the battery current, battery voltage, battery power. So now I will come to the another solution: onboard charger with multi-phase machine. So in a multi-phase machine, here it is a 5-phase machine. So for 5-phase machine, this is the 5-phase inverter we required to charge the battery from the 5-phase machine. Then grid. This grid is required some arrangement. These are two switches. Hardware reconfiguration is required here. So these switches are open in charging, and machine is connected to phase A. Phase A of the grid is connected to the phase A of the motor winding, and phase B is connected to the midpoint or of the uh, phase B and phase E to supply half of the current. And similarly, phase C of the grid is connected midpoint of the phase C and phase D to supply half of the current of the grid, which is coming from the grid. So during the charging, so we can equivalent circuit we can see here. Phase A directly connected, phase B of the grid is connected to phase B and phase E of the motor, and phase C of the grid connected to the phase C and phase D of the motor. So again, onboard charger with 6-phase machine. If there will be a 6-phase symmetrical machines are there, so you can see here these switch S1 and S2 will be closed during the propulsion operation. It is open during the uh, uh, in a charging operation, and switch S3 will be closed in the charging. So some by using this, you can see equivalent diagram will be like this way. In charging, switch S1 and S2 are open, switch so switch yes, so switch S3 will be closed. So you will see here, you more clearly you can see here in this particular diagram. So phase A and E will be connected with simultaneously with phase A. Phase B and Z will be connected to phase B of the grid, and phase C and phase X will be connected to phase C of the grid. And in this situation, these switches will permanently turn on, and this forms the a 3-phase interleaved boost converter. Okay, so this is the beauty of the uh, this machine winding, how the machine winding and inverter are used in the charging circuit without utilizing extra converter. So now I will come to the another is solar PV based charging solution for the it is for the any e-boat application. So here solar PV and battery is used to supply the load of the boat. So it forms this converter operates sometimes as a boost, sometimes as a SEPIC. Okay, so there are different modes of operation in this converter. First, battery to load when solar PV is not available. This is the CISO mode, single input, single output. Then there will be a DSO mode, dual input, single output. It is only when PV is not generating sufficient power to the load. So battery and load both supply power to the battery, and PV supply power to the load. Okay. Then pseudo single input dual output, there may be a chance PV power is higher than the P load. So some required power is supplied to the load, and remaining power will given to the battery for the charging. If PV is generating more than P load, then pseudo mode will come. Again, CISO mode will come when PV is supplying power to the load. Okay, battery is, because there may be a situation battery is fully charged and PV is higher than the P load. So in that situation, MPPT will not take place. This is the graphical representation, thematic representation of the modes of operation. So operating modes we can see here uh, that CISO mode. So battery is this converter operates as a in SEPIC operation. This switch S1 is operated in a PWM, and this is the load voltage. It's governed by the conventional um, conversion ratio D upon 1 minus D. This is the single input dual output. Single input dual output means that when PV power higher than the P load, then PV is used to store the energy in this way, and when and it will charge the also battery here, or it will supply energy to the outside to the load. So this is the DSO mode. DSO mode means that battery and both battery and solar PV both is used to supply power to the load only. Okay, so operation is again very simple, and battery is will stores the energy in inductor L2, and if here there is a situation, this is the switch D1 is the duty ratio of the switch S1, D3 is the duty ratio of the switch S3. If D1 is greater than D3, then state 2 means this will occurs. If D1 is less than D3, then this state will come into the picture. So both sources are supplying power to the load, and the operation is again either in a SEPIC mode or a boost mode. This is the a relevant waveform of this converter. So this is the reference power. See it. It is interesting. So here CISO mode. So CISO mode means that solar PV is not generating any power. So battery is completely discharged. Battery will only discharge when solar is generating power, but it is not sufficient power uh, for the load. So battery will discharge, and battery will also discharge, and solar also supply power to the load. When PV is exactly generating power to the load, so CISO with MPPT means whatever the reference power and solar PV power met, the battery will not discharge, its SOC will constant. So again, if CISO mode, CISO mode means that solar PV is generating much power than the load power. So it will supply the load power as well. Battery will charge. When battery will fully charged, so PV will only supply power to the load. So in that situation, MPPT will not take place. So this is all about from my side. If audience has any question, they can ask.
Any question from audience side?
If they don't have any question at present, they can ask later via email, and can give can share my number also with the audience, so that they, if anything they want to discuss about these works, they can discuss with me also for
Yes, sir.
their
Yes, sir. Yes, sir.
understanding.
Sure, sir. Okay. So I think audience have no question. So thank you so much, sir, for such wonderful session on solar PV and grid-based onboard charging station for EV system. Your clear explanation, real-world example, and expertise have truly and imagine the value in this 2 week ongoing faculty development program. We sincerely appreciate your effort and expertise. Thank you so much, sir.
Thank you. Thank you.
Thank you, sir. Session has already completed, so I now request every participant to kindly they can leave the meeting, and they are requested to join tomorrow again at the same time 5 p.m. tomorrow for the next session. Thank you. Thank you everyone.